Welcome Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. And in this lecture we are going to derive and then utilize the Capstan equation. Now this is a very classic equation that basically tells you what the transfer rate, and rate not in terms of time but in terms of wrap angle of a cable or a rope around a mandrel in terms of transferring tension in the cable via friction to a tangential force around the mandrel itself. So we're going to basically unload a rope through friction to the surface of a solid rigid mandrel. And we are going to derive a relationship for how much tension we still have in the rope based on the wrap angle that we've made. And so of course wrap angle can be just about anything. It could be 20 degrees or it could be 6 times around, which is 6 times 2 pi. And as a warning, I shouldn't have even said the word degrees, because all of our angles for the Capstan equation and its derivation are in radians. So the angle needs to be in the dimensionless, unitless radians format. So all the way around is 2 pi, not 360 degrees. Just as a warning, that is a very good way of getting the problem wrong if you throw degrees into the angular part of the Capstan equation. Okay, so we're going to start with a lot of viewing up and down, because these are somewhat detailed little sketches. So we have a rope, and we're trying to slip the rope kind of in a counterclockwise direction around this mandrel. So a mandrel is like a round axis that's fixed, that doesn't rotate, and it's used to basically to fixture ropes and cables. And we're gonna kind of look at the wrap angle, and it goes from point P around here to P2, and that gives us an angle of B, or excuse me, of beta. So that's the total angular contact surface that the rope makes with the mandrel. Okay, and we're just going to consider for now angle theta between some central point in P1, and we're going to zoom in on a very small, but not infinitesimally small yet, but a very small little tiny bit of rope or belt. We could also consider this as a kind of a flat belt. It would work the same as a rope. So we're going to take this little kind of arced section, kind of almost a trapezoidal section with rounded edges out, and we're going to draw an FBD. And we can draw an FBD on anything, so it doesn't matter if it's big or small. So this is our delta theta. So that's the angle that we are subtending, and that's you know how you call that angles. So this is delta theta. So here's our rope element, and we can define some central point. Well, we've got a tension being applied to basically normal to the cut surface that we cut this bit out with, over here basically pointing somewhat downwards and to the right. And the angle that it's going to make with a line perpendicular to the normal from the mandrel here, this is the normal from the mandrel. And okay, so T is going to make an angle of, actually, if this is delta theta, this angle is delta theta over 2. And so is that one. This is bilaterally symmetric. We know that the tension on this side is not quite the same, because we know it's trying to slip. So this bit is trying to kind of go to the left. So we know we've got a friction force going back to the right. And that friction force we can call delta F, meaning it's the friction that's being applied over this little bit of rope. So everything is deltas, meaning it's specific to this little chunk that we've cut out. It's very small. And we know that the normal force upward from the mandrel over that's being applied uniformly, pretty uniformly, over this little surface on the bottom of this bit of rope or bit of belt, we'll call that delta N for normal force. Okay, so we know the tension pulling back the other way is not necessarily the same as T, because we've got another horizontal force. So we're going to call it T plus delta T. And we don't know what delta T is, but we know it's different. And what it says is it's merely the difference between the tension on this side of the little bit versus this side. We've changed the tension by delta T, by some increment. Okay, so there's all of our forces, our angles, normal force, tensions, friction force. We know their orientation, so we should be able to write an equation of equilibrium. And so we do. Let's add them up. So if we're talking about kind of basically the horizontal or tangential direction, and if we're going to define the direction of T as positive this way, positive, we can say that horizontally or tangentially we've got T times cosine of this angle, and then we're going to subtract its brother over here, T plus delta T, which is making the same angle. And then we're going to have to add in our delta F, which is also going in the positive direction. So there's the sum of the forces in the tangential direction. So we can do the same thing. We can add up all of the forces orthogonal to that, which is normal to the mandrel. So we've got obviously our delta N coming up from the mandrel, and then we've got the normal components of those tensions, these smaller components here, pointing straight back down towards the center of the mandrel. So we have the sine of that theta over 2 times T plus delta T and times T. So here's our equilibrium expression for our little bit of rope here. Okay. Well, this is great and this is true, but it doesn't honestly do us a lot of good. So what we need to do is we need to first simplify this, because doing any more mathematics on these trigonometric functions is going to be really nasty. And next, what we're going to want to do is kind of get tension and angle kind of expressed in terms of one another without any other unknowns. And then we're going to take that bit of rope and we're going to shrink it infinitesimally small and see how that simplifies things. And once we do that, we'll take infinitely small bits of rope and then we will add them all up all the way across beta. So first step, get rid of the trig functions. So how can we do that? Well, we're going to invoke the fact that we haven't shrunk our bit of rope down infinitely small, but it's still pretty small. Delta theta is a small angle. So we can approximate with fairly good accuracy for a very small angle sine of an argument like sine of x and cosine of x can be simplified in this way. So sine of its argument, which is delta theta over 2, is just delta theta over 2. So sine of x is approximately x if x is really small. Likewise, cosine of x is approximately 1. So if you think about the shape of the sine and the cosine function, if you're close to 0, cosine of something close to 0 is pretty close to 1. And if you look at the slope of the sine curve, you can make the same argument about sine being approximately equal to just what's on the x-axis. If you want to look at this formally and you're familiar with Taylor series, you can take the Taylor series expansion of cosine and of sine and then just lop off everything except the first term. And you'll find the first term is just the argument, or 1. So everywhere we see sine of delta theta over 2, we're going to just plop in delta theta over 2, and everywhere we see cosine of delta theta over 2, we're going to plop in a 1. So we're going to do that to our equations of equilibrium. And they look way simpler now. Now it's just very simple polynomial expressions. And we're going to take advantage of that and simplify, and so we can now say that our delta F, our little bit of friction, is going to be equal to our delta T, which is significant in and of itself. And we can say that we can have a relationship between our bit of normal force and then tension and theta. So that certainly helps. So we've now got two expressions. Here's our kind of our vertical, and here was our horizontal. Okay, looking better, but still not at the point where we're ready to start shrinking down that delta theta to a differential element, to infinitely small. So next what we can do is we can drop in our imminent slip, because that's really what we're concerned with, is at the maximum how much load can we transfer. So we're going to invoke imminent slip and say, okay, the maximum that our delta F can be is mu sub s times delta n. Can't get any bigger. So that's the most, effectively we're saying that's the fastest we can transfer tension from the rope to the mandrel. Okay, so we put that in, and so we immediately, when we drop that in to this expression, we get that. So we now have a direct relationship between delta n and delta T mu s, and we plug that in for delta n in our vertical equation, and we get this single expression. And so we're gonna grab everything that has a delta theta in it, because we're concerned with total angle. We're going to stick it on the left, and we're going to take this one term that doesn't have a delta theta and stick it over on the right. Now draw a box around it. So now we have an expression that relates tension, angle, change in tension, and coefficient of friction. Now I'm ready to make my next simplifying step, and to do that, that step's going to allow me to get rid of this middle term here. We got to get rid of this. I'm going to get rid of this by shrinking our delta theta down to infinitesimally small. So instead of just having it be small enough to invoke this trig simplification, I'm going to shrink it down to what's known as a differential element. So it's going to go infinitely small. So I'm going to take the limit of this expression that I just boxed, and I'm going to look at what it turns into in the limit as delta theta goes to 0 and becomes d theta, becomes an infinitely small angle element. Well, the first thing that happens is I replace all the delta thetas with d thetas, and my kind of finite but very small change in tension is going to become a differential, an infinitely small change in tension that results from all this, and we're going to see that over here. Mu sub s is a constant regardless of what we do, and we're going to have another d theta here. So one of the things to consider is thinking back to your limit theory if you've taken differential calculus. When you're looking at something very, very small or large, one of the ways that you evaluate limits is to say if something is heading towards, say, infinity and it's multiplied by something else that is, there's a concept that it'll get there faster. If it's multiplied by something else, it's very, very large. The same thing happens with the argument of things that are getting very, very small. And what we can and can't neglect. We've got dt and d theta being multiplied by one another. They're both getting extremely small. They're approaching 0. They're not 0 yet, but they're approaching 0, and that's what this little arrow means. It means approaching. Something approaching 0 times something else approaching 0 gets to 0 faster than something that's just approaching 0 by itself. So it's kind of an expression of limit theory. So what that does is it allows us to neglect this term. This is going to be inconsequential compared to these other two. So this is called a higher order term because it has two things that are approaching a limit multiplied together. So this just goes bye-bye, and we're left with this expression. So any of you who have taken integral calculus will know, aha, this is easy to integrate. That's great because we're going to use integration of this expression to add up the tension changes. This is a change in tension divided by tension at any point as we add up all the bits of angle from one point to another point that's the end of our total number of wraps. So we're going to add this, we're going to add the d thetas up over our entire beta arc that we defined at the beginning. So I'm going to integrate this expression. I'm going to add up those bits of angle with an integral. So here I'm going to integrate with respect to theta from the first angle where of my rope contacts or my cable contacts the mandrel to the point where it leaves it. So theta 2 minus theta 1 is beta. And likewise I'm going to integrate this side with respect to t. dt means integrate with respect to t. And I'm going to integrate from the tension in the rope that corresponds to the point where I first contact the mandrel to the point at theta 2 where the rope leaves the mandrel. So tension when the rope hits the mandrel, it goes around and around and around the mandrel, and then the tension in the rope when it's done, when it's leaving the mandrel again and going somewhere else. Okay, so I evaluate this integral. So basically the integral of a constant with respect to theta is just going to be theta, and I'm going to evaluate that between these two limits. The integral of 1 over t with respect to t is natural log of t, and I'm going to substitute in both tensions. So one thing we notice with our units, and this is why theta has to be in radians. The natural log of anything ends up being a unitless expression. There's no units that carry through the natural log. So theta 2 and theta 1 have to be in radians. So it's going to be some fraction of pi or multiples of pi. And of course we know our coefficient of static friction is unitless. And so we also know we can define the angle where the rope departs the mandrel minus the angle where it enters and starts contacting the mandrel. This is beta. So this is our total angle of contact. So mu sub s times our total angular contact is going to equal the natural log of the ratio of our tension when the rope leaves to our tension when the rope enters. So basically just equate before and after. So if I don't want to use a natural log, usually I'm solving for tension, so I'll take the exponent of both sides and I'm left with this equation, which is the Capstan equation. So exponent of our coefficient of static friction times our total angle of contact is going to equal our ratio of tension in the belt or rope for positions 1 versus 2. And it's dependent on, notice, just on mu sub s and the angle beta in radians. Okay, so this is the Capstan equation right there. Very simple. So this is a way to account for friction when we're trying to unload a rope. So we can use that in some problems. Okay, fixture things a little bit. So here's our first use of it. We got a weight sitting on a ramp, and it's got some friction, and we've got a mandrel, and we've got a cable running over the mandrel, and it's contacting it over an angle beta, which we're going to have to solve for with some geometry. And we've got a different friction, rope on mandrel, than block on slope. So we got a lot of friction with the block on the slope, and it didn't go anywhere. And we're going to lose some of the tension we need to pull that block with the friction on the mandrel. And somebody says, okay, well, I gave you the coefficients of friction, and you know the geometry, you know the angles. So how much weight do I have to add? How hard do I have to yank on that rope, given all the frictional losses, to make the block just ready to slide? So we want to know the weight of A, which results in incipient slippage. Incipient slippage. That means I can invoke F equals mu s times n. So I automatically just bought myself another equation. Incipient slippage also means I'm entitled to use the Capstan equation, because invoking of that was something, remember, that we did when we derived the equation. So unfortunately, if we're not at imminent slip, at least with respect to the rope on the mandrel, we can't necessarily use it, but we can because somebody wants to know what's going on under those conditions. Okay, so first thing we're going to do is a little bit of geometry, because we've got to solve for beta given the rest of the geometry of the problem. So we can take a look and use some vertical angles here and look at the way things are oriented. And we know that this is basically vertical. So we have a 90-degree angle there. This is tangent at this angle. So basically, if I were to draw a normal here, I'm just basically working out how I got the geometry. We can use our concept of geometric vertical angles, and adding up to 90 degrees beta is basically related to this angle, 90 degrees to this one. So go through our angle, add up, and we find that beta is actually 90 degrees minus the angle made on the slope. So our a tan of 5/12. So basically that's how we get beta, which is absolutely imperative for using the Capstan equation. And so the first thing we do is convert it to radians, so we don't make that mistake later on. So the next thing we're going to do is we just derive the Capstan equation, so we really want to use it. And that is important because now the tension in the rope is not uniform through the rope. So down here, the tension in the rope is equal to the weight of A. But up here, we're going to transfer some of that tension to the mandrel, and so it's going to be somewhat less up here, so we're not going to have the full weight of A pulling on our block B. So let's go and figure out how much we got. So we're going to invoke the Capstan equation. We got a mu sub s of 0.4. We know that T2, our weight hanging downwards, our full max tension, is the weight of the block. So it's the weight of A. And so we know that at the T1 that we're going to apply to block B is going to be related to T2 by exponent of our mu sub s of 0.4 times our beta angle, which is 1.176 radians. So if T2 is the weight of A, we can get T1 is weight of A divided by a single number that we can calculate. So now we have an expression for T1 in terms of the weight of A, the thing we wanted to solve for, that we can go ahead and apply to the block. So now I'm going to FBD the block. So I got T1 pulling the block down, and we know that T1 is related to weight A through the Capstan equation that we just went through. We have coordinates that are tangent and normal to our slope. So I've got the weight of my block, 20 newtons, and I've resolved that into normal and tangential components. I've got a friction force just between the block and the ramp, pushing the block back uphill, basically, because the block's going to try to slip. And so that's going to be 0.6 times N1, which is the normal force of the block. So I can sum up forces in the tangential direction. So that's going to be friction force, upslope positive, minus 20 newtons times sine alpha, and remember alpha was this angle, which is a tan of 5/12, and we're going to be also subtracting the tension in the rope at this point. So this is our lessened tension after we went through the Capstan equation. We can get N1 through our sum of the forces in the normal direction. That's just going to be our 20 Newton weight times cosine of alpha, which we have. So we can solve directly for N1 out of this equation, and we can use that to get F through our imminent slip criteria for friction. We have alpha, and we now have an expression for T1 in terms of the weight. So we should be ready to go to solve for that weight. So here's the math steps that we go through. Here's our F in terms of imminent slip. Here's our N1 expression in terms of weight and cosine alpha. And so we've substituted those in, and then we have our expression for T2, weight A equaling T2, and then we've equated that with the Capstan equation for T1, and the rest of our terms coming out of the tangential equilibrium of the block. And just solve for A, we get 5.4 newtons. So you can work through the math yourself, but basically I just did one step where I used my Capstan relationship for T1 and then rewrote that to express T2. Okay. So that is our one example of our Capstan equation. That is it. You can do several more like it. I would highly recommend that for practice. Probably the number one biggest mistake that you make is mixing up which is the high tension and which is the low tension end of the rope, and not getting that in the right relationship. But it's really easy to remember that the tension before is going to be bigger than the tension after, and take a look at the exponent function and remember that beta is always going to be positive and mu sub s is always going to be positive. So the exponent function is going to increase and be fairly large and greater than 1 for its argument greater than 0, basically. So that can give you a little bit of a guide if you've gotten something wrong. Also remember that beta can be more than 1 rap. It can be pi over 4, it can be 16 pi, so it can basically go around the rope 8 times, it can go around the mandrel 8 times. So that's another way that you can look at it. So if somebody says, I wrap the rope around the mandrel 3 times, you know that's 6 pi. And put that in radians, and you are ready to know how much your tension is going to go down. And so that is it for friction with our application for the Capstan equation and tension attenuation for a flexible cable.